In this video, we're going to be going over graph traversal, and we're specifically going to go over BreadthFirstSearch, which is known as BFS. So we've talked about the terminology of graphs, what are the types of graphs, what are the types of components of graphs. We've also talked about a couple different ways that you could represent graphs, and then also how you could even implement the graph class in all the different options and data structures and abstractions you could use. So now, assuming that you have some graph that's set up some way, we are going to be talking about how to traverse a graph. Traversing a linked list, for example, particularly a singly linked list, is pretty straightforward. There's only one way to go, so you start at the front and you just keep going forward. Obviously, if it's doubly linked, you have a couple other options. Binary search trees, we talked about how you can traverse in three ways: in order, post order, or pre-order. For graphs, there's a lot of different ways, and as we talked about, because graphs have cycles, we have to be a little bit more creative in how we write our algorithms to traverse graphs. There's two main traversals. One is called breadth first and one is called depth first. We're going to talk about breadth first in this video, and then in the next video we'll go over depth first. A breadth first search is a very organized way to search for something. In a breadth first search, if you were perhaps to drop something on the floor underneath you, a breadth first search would be to basically start where you're at and go in like radial circles around where you're at and search in that way. A depth first search would be to go out and come back and search in that way. So those are like generally the two ways. So breadth first search on a tree, for example, and you can think about both of them on trees, would be to go by level. So start at the root, then search the next level of children, the next level of children, and then the final level of children. So breadth first search is this organized way of kind of like expanding out. So visually, if you have a graph, this is what breadth first search looks like. If you're starting at 0, you search at itself, and then you radiate out to its neighbors, and then you go one by one and visit their neighbors, which will give you the next circle, and then you go out and search their neighbors, which gives you the next circle. So visually, that's what it looks like. So what we're going to be talking about in this video is algorithmically how you actually write that. So the pseudocode for breadth first search is that you have to use a queue. So the queue starts off with the initial node that you're starting at, and the basic algorithm is that while the queue isn't empty, you're going to dequeue a node off the front, you're going to process that node, and then for each neighbor of that node, you're going to search it, and if the node has never been queued, you're basically going to add it to the queue. And that's like the basic idea of the structure. So the queue is used to keep track of how you're visiting those radial circles. Now, you need a few more abstractions to actually implement this algorithm, but let's just walk through it once on our own. So we're going to start at 0. So that's going to be the first node that we visit in breadth first search. The next node is going to be its first neighbor that you visit. So let's assume that we're visiting in order of like ascending order. So 1 is the next one out of its 4 neighbors. So its neighbors are 1, 2, 3, and 5. So we'll visit 1 first. Next we have its second neighbor, which is 2. Then we have its third neighbor, which is 3, and then we have its fourth neighbor, which is 5. Now we're going to go to each of those neighbors, which have all been queued, and we're going to then visit their neighbors in the order that we visited them. So remember, we visited 1 first because it was the first one. So we're going to go ahead and visit all of 1's neighbors, but 1 doesn't have any neighbors that we haven't already visited. It has neighbor of 0, but it also has the neighbor of itself, but we've already visited both of those, so we're done with 1. So now we're going to go on to 2. 2 has 1 neighbor. that hasn't been visited, which is 7, so we're going to visit that. And then we're done visiting 2's neighbors. Now we're going to visit 3's neighbors. 3 has one additional neighbor that we haven't visited, 4, so we're going to go ahead and visit that. Now we're done visiting 3's neighbors. Next in the queue is going to be 5. That was the 5th one that we visited. So 5 does have a neighbor. It has 6, so we're going to visit 6. And then we are done visiting that like inner circle's neighbors. So now we need to go to the outer circle's neighbors. So the first one that we visited was 7. That's still in the queue. So 7 does have a neighbor. It has the neighbor of 8, so we're going to visit it. And then our queue is actually still has a couple of nodes in it, so we would go through and visit all of those and see that 7, 8, and 9 don't have any neighbors, and so we would be done. And so the order of breadth first search for this graph would be in this order, and they're numbered on the graph as well. So that's how generally breadth first search works. So it's easy to do on small graphs that you can kind of see these connections in these radial lines, and as was drawn in the last one, we visited these neighbors, then we visited these neighbors, and then we visited these neighbors out. But oftentimes it's not easy to see that, and so you need a little bit more of an algorithmic approach. So we know that we need a queue to keep track of those nodes that we were visiting. So back here, we needed to know after we visited 0, it has 5 neighbors, right? So we needed to know, well, which of those neighbors do we go to first to visit their neighbors, right? So the queue is going to keep track of each of those neighbors. And you'll see later that when we do depth first search, we're not going to be able to use a queue, we're going to be using a stack. A second abstraction that we're going to need to use is a set. So I kept saying that the only neighbors that we haven't visited yet, well, we need to know that we haven't visited the nodes yet. And so in order to do that, we're going to use a set to keep track of not revisiting the same node over and over again on these searches. And that's really the key to graphs. That's the thing about graphs that's very different from tree traversal, is that you have to make sure that you don't keep revisiting nodes because there's cycles all over the place. The set that you use could be implemented with a hash or with a tree, so it could be used using the set or the hash set in C++, depending on what would be more efficient for the particular data that you're dealing with. So what we're going to do is actually go through the algorithm, the pseudocode of the algorithm, including the set, so you can get a better idea of how we actually did that traversal using breadth first search that I showed you kind of with the radial lines. So we're going to start at 0. So we have a couple of things set up. We have a queue, which we call frontier queue. This is taken from Zybook, so it has like a similar syntax to it. So we're going to start by adding the first node to the frontier queue. So we just have a 0 inside of the queue. We're also going to add the first node to the set because we've already been there. Then what we're going to do is run through this loop and see what happens. So while the frontier queue is not empty, we're going to pop the first node off the frontier queue. So on the first iteration, the only thing in the queue is the starting node 0, so it's going to be popped off, and the visited the order that we're visiting will keep track of in the visited set. So this will just keep track of each node that we're visiting. So this is a vector of just which ones that we're visiting, or the order of which we're visiting them. The set is going to be just keeping track of the visited nodes so that we don't go back to one that we already discovered. So visited is basically going to keep track of this as we build it. Okay. So what are 0's neighbors? Well, 0 has 4 neighbors. It has a 1, a 2, a 3, and a 5 that it can get to. So what we're going to do is we're going to push all of those into the queue. So it says as long as the neighbors are not in the discovered set, add them to the queue and also add them to the set. So our queue is currently empty because we just popped off the only node there. So our queue is now going to have those neighbors in it. And then our discovered set is going to be added to, and now we have all those neighbors in the discovered set as well. Now we're going to move on to the next iteration of the while loop. So we're going to pop off the queue again. So now we're going to pop 1 off the queue. So our current v is 1. So that means that we have now visited, in our BFS search, we now have gone from 0 to 1. Now 1 has 2 neighbors. It has a neighbor of 0 and it also has a neighbor of 1. Based off of this loop, we're going to visit all the neighbors, but we're only going to visit them if they are not in the discovered set. But 0 and 1 are both in the discovered set, so nothing's going to be added to the queue and nothing is going to be added to the set. So we pop off again. Now we pop off 2. So now we've gone from 0 to 1 to 2. So that is our traversal through the graph. So we're now here. So 2 has 2 neighbors. It has a neighbor of itself and it also has a neighbor of 7. So we go through any of those that aren't in the discovered set, and we know 7 isn't in the discovered set. So we are going to add 7 to the queue, and we're also going to add 7 to the discovered set. Now we pop off again, and now we're going to visit 3. Oops, why did I erase that? I meant to erase. Okay, so we're at 3. So we've gone from 0 to 1 to 2 to 3. So that's our path so far when we do BFS on this graph. What is 3's neighbors? Okay, so 3 has a neighbor of 0, but it also has a neighbor of 4. 0 is already in the discovered set, so we're not going to go there, but 4 isn't. So we are basically going to add 4 to the queue and 4 to the discovered set. Now we are going to pop off again the queue. So now we're currently at 5. So this is where we are. So we've gone from 1 to 2 to 3, from 0 to 1 to 2 to 3 to 5. Same thing I showed you in the animation. 5 has 1 neighbor that it can get to. It can get to 6. Now 6 isn't in the discovered set, so we're going to go ahead and add 6 to the queue, and we're also going to add it to the discovered set. Alright, so now we're back up at the top of the loop. It's not empty, so we're going to pop off again. We're at 7 now. So we've gone from 0 to 1 to 2 to 3 to 5 to 7. We're currently at 7. And we can look at 7. 7 has just 1 neighbor. It has the neighbor of 8. No, it has 2 neighbors. It has the neighbor of 4 and it has the neighbor of 8. 4 is in the discovered set, so we're not going to revisit, but 8 isn't. So we're going to add 8 to our queue, and we're also going to add it to the discovered set. All right, now we're going to pop off again. It's not empty. Now we're at 4, so we're visiting 4. So we have gone from 0 to 1 to 2 to 3 to 5 to 7 to 4. Let's see, 4 only has itself as a neighbor. It can only reach itself. So since 4 is in the discovered set, we are not going to revisit it. And the discovered set isn't going to change, so I'm just going to write from 0 to 8 there. Pop off again. We're now at 6. So now we've gone here to 6. So we've gone from 0 to 1 to 2 to 3 to 5 to 7 to 4 to 6. I'm going to need to erase that. That's bothering me. Okay, so we're at 6. 6 has one neighbor. It can reach 1. 1 is in the discovered set, so we are not going to put it into the queue. So we're only left with 8 in our queue. We're going to pop 8 off. 8 is our current node, so we're visiting 8 now. So 0, 1, 2, 3, 4, 5, 7, 4, 6, and 8 is the order that we're visiting the nodes. So we went from 0 to 1 to 2 to 3 to 5 to 7 to 4 to 6 to 8. Let's see, 8 has no neighbors, so that's going to be empty. And so there's nothing going to be added to the queue, so it's going to be empty. And our visited set is full. So now we have an empty queue. So our while loop stops and we are done. We've visited all the nodes. So that is a walkthrough of how BFS actually works and how you actually implement the algorithm with the queue in the set. It's sort of non-intuitive because you're adding stuff to the discovered set before you actually visit the node technically, so it helps to walk through the algorithm once to see that. As far as implementing BFS, we talked about implementing the class in the last video. The function for BFS would actually typically be set outside of a graph class. So this whole thing that we just wrote would be some function that you would write that you would pass in a graph that you have written in a separate graph class, but it would not necessarily and not naturally be as like a member function to a particular graph class. And this is something that you also see in C++ with the algorithms library, is typically separate from the class itself. Let's talk a little bit about efficiency of BFS. It's something we can talk about regardless of representation. Again, n nodes, m edges is the typical convention that's used when talking about graphs. The average work done per node has like a base work of 1. And then depending on how many edges the node has, there's additional work to be done, right? So in the algorithm, you could assume that if you have m total edges, that on average each node will have m over n work in processing those edges. That is an approximation, assuming that if you took the edges and divided by the number of nodes, that would be how many edges there were per node. And so if you have n nodes, the total work done is going to be the base work plus the m over n work. So the total work done for BFS is m plus n, which is a solid complexity. What we call when we talk about graphs is that BFS is a linear term algorithm because it is relative to the m plus n. Now, as I said before, I actually think I said the opposite, but I meant this. Breadth first search will depend on the implementation itself. So this is the breadth first search complexity for an adjacency list. So a great thing for you to think about is what would be the complexity of breadth first search if we were using an adjacency matrix? Adjacency matrix is, there's a couple different ways to do it, but doesn't depend as much as the adjacency list implementation. So that's it for BFS. Thanks so much.